Hello everyone, welcome back to my channel. So in this video we will see what is Hooke's law, Young's modulus, and also we'll solve some numerical problems related to stress, strain, and elongation and percentage increase in the elongation, and also some problems related to Young's modulus. Okay, so first of all, before I get into Young's modulus, I'll talk about Hooke's law. So generally Hooke's law states that the strain of a material is directly proportional to the applied stress. So indirectly, in short, people say stress is directly proportional to strain. Yes, so sigma is proportional to E, which means that stress is proportional to strain. Okay, so if I remove the proportionality constant, proportionality, I have to put a constant. So sigma will be equal to E into E. From here, E is called as Young's modulus or constant of proportionality or modulus of elasticity. So we will talk about this E in our next few minutes. So Hooke's law states that stress is directly proportional to strain up to proportionality limit. So about proportionality limit, I have talked in stress strain curve for mild steel video. You can look there. Next, coming to Young's modulus, as I've told, so we have, according to Hooke's law, stress is directly proportional to strain. So from here, if I remove the proportionality, I'll put a constant capital E, which is called constant of proportionality or Young's modulus or elasticity modulus or modulus of elasticity. So from here, capital E is equal to how much? Sigma by epsilon. So stress by strain. So Young's modulus is defined as ratio of stress to strain of a material. Actually, it is the capacity of a material to withstand the compression or the elongation with respect to its length. Okay, so Young's modulus gives us the relationship between the stress which is applied on the body and the strain which is in the form of a deformation. So this Young's modulus is named after the British scientist Thomas Young. So when any solid object deforms, when a particular load is applied on it, uh, if the object is elastic, of course the object will regain its original shape once you remove the load. So most of the materials are not linear and they are not elastic beyond a small amount of deformation. Hence, remember, Young's modulus applies only for linear elastic substances. So you can see the formula, it is sigma by E. So stress has the units of Newton per mm square because it's load by area. Strain doesn't have any unit, so indirectly stress and Young's modulus carry the same units. So now we will solve some numerical problems related to stress, strain, involving Young's modulus also. Okay. So first we have the first problem you can see here. So a rod 200 centimeters long and diameter 3 centimeters is subjected to an axial pull of 30 kilonewton. The Young's modulus is 2 into 10 power 5 Newton per mm square. Determine stress, strain and elongation of the rod. So first, let's write off the given data first. So what is he telling? He's telling that so the length of the rod L is given by 200 centimeters. So better we will convert this into mm. So this becomes 2000 mm because it is 200 into 10. Next is we have dia of the rod which is 3 centimeters. I'll convert this again into mm, so which becomes 30 mm. And axial pull is given, means which is capital P, which is equals to 30 kilonewton. So I'll write this as 30 into 10 power 3 Newton because I'm going to write everything in Newton per mm square. Next, Young's modulus of the metal is given, which is capital E, which is equal to 2 into 10 power 5 Newton per mm square. Now let's see how can we calculate the stress, strain and elongation. So before I calculate the stress, let me calculate the area of the rod, which is given by the formula pi by 4 of d square. So this is equal to pi by 4 of what is d? 30 whole square. So we would get area of the steel rod as 706.86 mm square. Now we will calculate the first part of the question, which is stress. So generally, what is the formula for stress? Stress is equal to load by area. So it's simply P by A. So what is P? 30 into 10 power 3 by area is 706.86. So if I divide load by area, I would get stress value as 42.44 Newton per mm square. Similarly, let's go for the second part of the question, which is strain. So strain is generally given by the formula change in dimension by original dimension, but here we don't have anything related to change in length. That's what is we need to calculate. So for this strain, you can apply the relation of this, as we have discussed. Sigma is equal to capital E into strain. So from here I can write strain as sigma by capital E, because I have the value of sigma and capital E is given in the question. So we have, generally the formula is Young's modulus is equal to stress by strain. So from here strain will be equal to what? Stress by Young's modulus. So I'll just substitute and get the answer. So stress I got 42.44 by Young's modulus is 2 into 10 power 5. So let's see how much would be our strain value. So it is 0.00021. And let's go for the third part of the question, which is elongation of the rod. So elongation of the rod is what? Change in length, which is nothing but the delta L, because it is subject to axial pull. So you will get increase in the length, which is delta L. So for this, let's take the basic formula of strain, which is what? Change in length by original length. So from here I already know strain value as 0.00021, which is equal to, this is what change in length I need to calculate, delta L by what is original length given, 2000. So finally what can I write delta L as? 2000 into 0.00021. So finally I get the answer as around 0.424 mm. So like this we calculate stress, strain and elongation. So this is a very basic model problem, just for practice I have told. Now let's see another problem which is important. So you can see here a tensile test was conducted on a mild steel bar, and the following data is given to us regarding the test. So we have diameter of the steel bar given. So simultaneously while explaining the question itself, I'll write the given data. So in short, I'll write the given data. So you can see here dia of the steel bar is given as 3 centimeters, and we will better convert this into meters. Okay, so it becomes easy for us. So this becomes 3 by 100, which is 0.3 meters. Okay, sorry, 0.03 meters. Okay, because it's 3 by 100, right? So just a second. So yeah, so it is 3 by 100, 0.03 meters is the dia. Next is gauge length. So gauge length means that it's the original length, which is how much? 20 centimeters, which is 20 by 100, which is equal to 0.2 meters. Next I have load at the elastic limit. So load at elastic limit is, we'll write it, load at elastic limit is equals to how much? 250 kilonewton, which is equals to 250 into 10 power 3 Newton. Similarly, I have extension at a load of 150 kilonewton given. So extension at 150 kilonewton is how much? 0.21 mm. So this becomes, mm should go into meters. So 0.21 into mm 2 meters is 10 power minus 3 meters. Okay, next. Maximum load is given. So maximum load is equals to how much? 380 kilonewton, which is equals to 380 into 10 power 3 Newton. Okay, what else is given to us? Total extension. So total extension is equals to, means the final extension or the complete expansion what has taken place was around 60 mm. So which is equals to 60 by 1000, since I'm writing in meters, so this becomes 0.06 meters. And we have diameter of the rod at the failure, let me take it as small d, which is equal to 2.25 centimeters, again 2.25 by 100, so 0.0225 meters. This is the entire given data. He's asking us to calculate Young's modulus capital E, stress at elastic limit he's asking. So you should calculate sigma at elastic limit, percentage elongation. when compared to the original length, and percentage decrease in area. Before it is failing, it is the area is decreasing, right? So for that, what is the decrease? So first, before we get into the problem, first let's calculate area of the steel bar, means the original area. Okay, so original area is given by capital A, which is equal to pi by 4 of original diameter, which is pi by 4 of 0.03 whole square. So this comes around 7.06 into 10 power minus 4 meter square. So first I have calculated the area. So once you finish the area, we will go to the first part of the question, which is Young's modulus. So what is the basic formula for Young's modulus? We have Young's modulus is equal to stress by strain. So to get Young's modulus, remember one point, we have a load at the elastic limit, which is 250 kilonewton, but the load at elastic limit is given as 250 kilonewton, but the extension is not given to us to calculate the Young's modulus. But if you see this 150 extension at a load of 150 kilonewton is given, means indirectly at a load of 150 kilonewton the deformation is 0.21 mm. So from here, can we calculate Young's modulus? Yes, we can calculate. So let's take the formula of stress first. So stress sigma is equal to load by area. So I'm taking 150 kilonewton because I know the extension at that place. So this is 150 into 10 power 3 by, what is the area? It is 7.06 into 10 power minus 4. So from here, what is sigma value around? Sigma is 21246.45 into 10 power 4 Newton per meter square. This is the stress we obtained. What is strain now? So strain, E is equals to, or epsilon is equal to change in length by original length. What is the change in length at 150 kilonewton? 0.21 mm, which we converted as 0.21 into 10 power minus 3. What is the original length, actually gauge length? 0.2. So finally, what is strain now? 1.05 into 10 power minus 3. Now let's calculate Young's modulus capital E as stress by strain. So it is 21246.45 into 10 power 4 by 1.05 into 10 power minus 3. Let's see how much we get the Young's modulus. So we get Young's modulus around 2.023 into 10 power 11 Newton per meter square. So simply I can write this as 2.023 into, I'll write this as 10 power 11 as, better I'll write it as into 10 square into 10 power 9 Newton per meter square. So 2.023 into 100 is around 202.3. 10 power 9 Newton per meter square is called giganewton per meter square. So this is just simply I wrote. You can stop till here also, no problem. Now we will see the second part of the question, which is stress at elastic limit. Particularly they are asking us what is the stress at elastic limit. Okay. So let's see what is the stress at the elastic limit. To calculate stress at the elastic limit, what should I know? I should know the load at the elastic limit by area. Is the load at the elastic limit given to us? Yes, load at the elastic limit is given as 250 kilonewton. By area, if I put capital A this value, I will get the stress. So sigma elastic is equal to load at elastic limit divided by what? Area. So finally, this is 250 into 10 power 3 by, what was the area we got? 7.06 into 10 power minus 4. So finally, we get sigma elastic as, which is around 354.10 into 10 power 6 Newton per meter square. 10 power 6 Newton per meter square is called megapascal or mega Newton per meter square, correct, megapascal. So this is sigma elastic. So I am done with the second part of the question also. What is the third part of the question now? percentage elongation. So what do you mean by percentage elongation? So percentage elongation is, so I'm giving the heading here, percentage elongation. Simply elongation means we calculated delta L, but it is, they are asking in terms of percentage. So when you're talking in terms of percentage, so percentage elongation is given by the formula total increase. I mean to say total, what is the change in elongation? So total increase in length, or you can say it is total elongation divided by what is the original length, okay, into 100 will give you the value of percentage elongation. What is the total elongation or extension given to us in the question? 60 mm, which is 0.06 meters. So it is 0.06 by what is the original length? 0.2. So into 100. Just this is change in length by original length only, no, but into 100 we are doing because we want percentage, as simple as that. So you get around 30%. And let's calculate the last part of the question. So what is the last part of the question? We need to calculate the percentage decrease in area. So percentage decrease in area is given by the formula, again, percentage decrease in area is equals to how much? Original area minus area at failure, okay, by original area into 100. Because you may ask me, why are we doing this area of failure? Because at area of failure, what will happen? The area will decrease, no? So original area minus area of failure by original area into 100 will give you the value of percentage decrease. So what was our original area? Pi by 4 d square was the original area. Area of failure is pi by 4 of small d square. I have shown a clear differentiation between capital D square and small d square into 100. So this I already calculated as, here you can see 7.06 into 10 power minus 4. So 7.06 into 10 power minus 4 minus this we did not calculate still. Did we do for small d? No, we did not do for this value. So let's substitute that here. Pi by 4 of how much it is? Small d is how much? 0.0225. So 0.0225 whole square by again 7.06 into 10 power minus 4 into 100. If you do, you'll get the answer of percentage decrease as 43.68%. Got it, guys? Like this we have to solve. So stress is just load by area, strain is change in length by original length, Young's modulus is stress by strain. The only new thing what you have learnt is percentage elongation, which is total elongation by original length into 100, and percentage decrease in area, original area minus area of failure by original area into 100. Okay. Now let's see another problem, which is about varying cross sections. So here you can see here, this is bars of varying cross section. You have 3 different sections in a given bar, which are of different dias and different lengths, and they form a complete one single section, one single part. And he is telling that there is an axial load of 35,000 Newton acting on either sides. Okay. So Young's modulus of this complete composite section is given. He is asking us to calculate the stress in each section. Means section 1, what is stress? Sigma 1, sigma 2 and sigma 3. And also he is asking us to calculate total extension of the bar. So this bar will deform individually, this bar will deform individually, this bar will deform individually. But since they are fabricated together, you should calculate the total deformation because of this load. Okay. So this is what we will be solving in this problem. So first let's write the given data, all of you. So first P is how much? 35,000 Newton. Let it be like this. Next we have L1, which is 20 centimeters. Let's convert this into mm better. So into 10. Okay. So it is simply 200 mm. Similarly, what is D1? 2 centimeters. Again we will convert this into meters, which is mm, which is 20 mm. Similarly, let's write for L2. L2 is 25 centimeters, so which is 250 mm. So what will be D2? 3 centimeters, which is equal to 30 mm, because 1 centimeter is 10 mm. Similarly, let's write for L3. So L3 is 22 centimeters, which is equal to 220 mm. So from here, next is D3. D3 is how much? 5 centimeters, so which is equal to 5 into 10, 50 mm. So now our intention is to calculate sigma 1, sigma 2, sigma 3 in the first part of the question. So before I go into that, let's calculate A1. So which is pi by 4 of d1 square. I always suggest you people, once you have dias, please calculate the area immediately, cross-sectional area immediately. Similarly, A2 will be pi by 4 of d2 square, which will be equals to pi by 4 of d2 is 30 whole square. Similarly, A3 will be equals to pi by 4 of d3 square. So which is equals to pi by 4 of 50 whole square. So I'll just calculate the values and I'll write the answers. Alright people, so I have written the answers for A1, A2, A3. You may have a decimal that's it outside, but you should be closer to these values. Now let's start off with the first part of the question, which is stresses in each section. So I'm giving the heading stresses in each section. So we need to calculate the values of sigma 1, sigma 2, sigma 3. The concept is very simple. We have the formula for sigma as P by A. Just now we have seen stress is load by area. So from here, stress in first section or stress in section 1, sigma 1 will be equals to P by A1. Why I wrote P only? Because you can see in the entire figure there is only one tensile load, which is P. So area is different. So that's why I wrote P by A1. If P1 is also different, you should write P1 by A1. So finally, what is sigma 1 equals to? P is 35,000 by, what was A1? 314.15. So let's see how much we get the answer of sigma 1. So sigma 1 is 111.41 Newton per mm square. You must be closer to this, okay? Next, let's calculate stress in section 2, sigma 2, which is given by the formula P by A2, which is again equals to how much? 35,000 by, what is A2? 706.85. So let's see how much we'll get this answer. So this answer is around 49.51 Newton per mm square. Similarly, let's calculate sigma 3. So P by A3. So sigma 3 is equals to 35,000 divided by A3 is how much? 1963.49. So 1963.49, if I divide with 35,000, I got around 17.825 Newton per mm square. So the first part of the question is simply done. Stresses in each section, sigma 1, sigma 2, sigma 3, we calculated using basic formula. Second part is total extension of the bar. Means you need to calculate total value of delta. For this, what we will do? So total extension of the bar they are asking, the complete bar they are asking. So what you have to do? You have to calculate the extension in the first section, then you have to calculate the extension in the second section, extension in the third section, and add. You will get the total extension because of this 35,000 Newton. Because it is only single load, I will write total extension directly. Okay, delta L as what? Plus delta L3. So this is elongation in first section, second section, third section. If I add, I will get the total elongation or extension. So delta L will be equal to, what is the formula for extension? It is given by the formula of PL by AE. You may ask how we got this. So I'm just doing it the below. See here, we have sigma is equal to P by A, right? Load by area. And we have strain as change in length by original length, correct? So if I write for say suppose Young's modulus, what is Young's modulus equal to? Stress by strain, correct? So it is P by A divided by delta L by L. So finally what will I get? I will get PL by A into delta L. So from here, if E is equal to PL by A into delta L, what will be delta L equal to? This E will come here, PL by A. This what is the reference formula I have used, I have written here. I didn't write P1 because P is common. Similarly, this will be PL2 by A2 into E. Even Young's modulus is also same. Next, PL3 by A3E. If you have different values, you should write P1L1 by A1 E1, P2L2 by A2 E2, P3L3 by A3 E3. What can I take common from here? I can take out P by E common. So I am left inside with L1 by A1 plus L2 by A2 plus L3 by A3. So I'll substitute all the values. This is 35,000 by what is E? E is 2 into 10 power 5, but actually it is in Newton per mm square, right? So we have converted everything into mm. I forgot. So it's 2 into 10 power 5. What is L1? So L1 is 200 by A1 is 314.15 plus L2 is 250 by this is 706.85 plus L3 is how much? 220 by this is 1963.49. So just put up in a calci and get solve it. You will get delta L as 0.183 mm. This is the answer. Okay, so like this you have to solve for bars of bearing cross section when there is only one single